At dawn, the Great Pyramid does not look like a mathematical problem. It looks like a mountain that has forgotten how to erode. Its flanks rise out of the Giza Plateau in broad, weathered steps, their once smooth casing mostly stripped away, their edges softened by 4.5 millennia of wind, heat, quarrying, earthquakes, and human intrusion. From a distance, the monument appears almost brutally simple. 4 triangular faces, 1 square base, a single point aimed into the empty sky. Yet the closer it is measured, the less simple it becomes. The sides are not perfectly equal. The faces are not perfectly flat. The summit is gone. The original outer surface survives only in fragments. The bedrock beneath it is uneven. Passages run into the stone at calculated angles. Chambers sit at different levels inside the mass, and voids still emerge from modern scans where earlier generations assumed there was nothing but masonry. The pyramid seems to offer a clean geometric form while withholding the exact geometry that created it. This is the contradiction at the heart of Khufu's monument. It is precise enough to provoke astonishment, damaged enough to frustrate certainty, and large enough that even a small error becomes a major question. A deviation of a few centimeters may sound trivial until it is stretched across a side more than 200 meters long. A tiny angular difference may seem negligible until 4 faces must rise toward one apex without drifting apart. The builders are not placing a polished object on a table. They are controlling millions of tons of stone across a footprint large enough to swallow several modern city blocks, while working with ropes, sighting tools, plumb lines, leveling methods, human memory, repeated checking, and a labor system that has left only fragments of its procedures behind. Before we go deeper, take a moment to like the video and subscribe if this is the kind of history and mystery you enjoy. The Great Pyramid's geometry is often described in language that goes too far. It is called impossible, supernatural, encoded with secret constants, or proof of knowledge that should not have existed in the 3rd millennium BCE. Those claims survive because the monument genuinely is extraordinary, but its real mystery is more demanding than fantasy. The question is not whether unknown beings handed mathematics to Egypt, or whether the pyramid hides a message intended for a distant technological age. The stronger question is how an old kingdom state translated measurement into stone at an almost unimaginable scale, how it kept correcting itself as the structure rose, and how much of the apparent perfection belongs to deliberate planning rather than modern reconstruction. Even the first measurement is difficult. Where, exactly, does one side begin? The original casing stones form the true outer face, but most of them were removed long ago. What survives today is largely the rougher core, exposed like bone after the skin has been stripped away. Near the base, scattered casing remnants and prepared sockets offer clues, but they do not produce an unbroken line. Surveyors must reconstruct the original footprint from fragments, cuttings, surviving stones, platform edges, and the geometry implied by what remains. Different measurements taken in different centuries do not always agree, not because the pyramid changes dramatically, but because the object being measured is incomplete and the method of measurement matters. The missing summit creates another uncertainty. The pyramid no longer ends in its original point, so its intended height must be inferred from the surviving slope and reconstructed base. If the slope varies slightly from face to face, or if erosion has altered the outer courses, the estimated apex can shift. That shift affects calculations involving the pyramid's perimeter, height, face angle, and the famous ratios often claimed to be hidden within them. A measurement that appears to reveal pi, or the golden ratio, may depend on which reconstructed base length is chosen, which height estimate is preferred, and whether the lost casing surface is treated as uniform. Scholars still debate where intention ends and numerical coincidence begins. Yet uncertainty does not reduce the achievement, it sharpens it. Modern surveys consistently show that the pyramid was laid out with remarkable control. Its base is close to square. Its faces align closely with the cardinal directions. Its corners were established across uneven rock with a level of consistency that remains impressive even after the surviving structure is separated from exaggerated claims. The north side is not simply pointed toward a vaguely northern part of the sky. The entire monument was oriented with an error measured in only a small fraction of a degree. The builders may have achieved this through repeated solar or stellar observation, but the precise procedure remains uncertain because no complete instruction manual survives. This absence of a manual is one of the pyramid's most powerful silences. Ancient Egyptian mathematics is not unknown. Surviving papyri show practical methods for fractions, areas, volumes, and slopes. Builders used a system known as the seked to express the horizontal run for a given vertical rise. This could produce the Great Pyramid's angle without requiring modern trigonometry or a written symbol for pi. But knowing that a workable mathematical language existed is not the same as knowing exactly how the builders applied it across every stage of construction. A design can be simple on a small diagram and brutally difficult on a rising monument, where each new course hides the reference lines below. The pyramid also refuses to remain a purely external shape. Modern non-destructive surveys have shown that its internal geometry is still being mapped. Cosmic ray muons, radar, ultrasound, and electrical resistivity have identified and confirmed corridor-like spaces near the north face. Other investigations examine the blocks in the king's chamber, not merely as visible surfaces but as volumes with hidden backs, joints, thicknesses, and internal reflections. The structure is therefore not a solved solid. It is an architectural body whose interior continues to be reconstructed without dismantling it. That changes the nature of the mystery. For centuries, the pyramid was treated as a finished form waiting to be decoded. Now it is increasingly understood as a layered construction whose visible shape, hidden spaces, materials, stresses, and later damage must all be studied together. Its geometry is not just the angle of four faces. It is also the relationship between foundation and chamber, passage and load, void and stone, planned symmetry and construction tolerance. The phrase that the geometry doesn't add up is useful only if it is handled carefully. The numbers do add up well enough to show that the builders understood proportion, orientation, leveling, and large-scale planning. What remains unresolved is how they managed error in practice, how often they adjusted the work, which dimensions were primary, and which elegant ratios were consequences rather than goals. No single explanation fully accounts for every measurement, every irregularity, and every hidden feature. The pyramid's power lies in that narrow space between what is measurable and what is recoverable. It is not beyond mathematics. It is a monument created through mathematics, yet the chain of decisions that turn numbers into stone has largely vanished. At sunrise, its shadow stretches across the plateau in a clean triangular form. Beneath that shadow lies a less perfect and more fascinating reality. A structure aligned with astonishing care, altered by time, incomplete in the record, and still forcing each generation to measure it again. To understand the Great Pyramid's geometry, the first task is not to admire the monument that survives. It is to reconstruct the monument that no longer exists. The pyramid on the Giza Plateau today is a stripped and wounded version of Khufu's original design. Its exposed core rises in rough horizontal steps, each course marked by blocks of different sizes and surfaces worn by weather and removal. The smooth white casing that once defined the true outer planes has almost entirely disappeared. The apex is missing. Sections of the base are obscured, damaged, or buried beneath later disturbance. Even the plateau around it has changed. Sand has shifted, stone had been quarried, pathways have been cut, and ancient construction zones have become archaeological landscapes. Any claim about the pyramid's exact proportions begins with an act of recovery. The original monument would have looked startlingly different. Fine Tura limestone casing stones covered the four faces, their outer surfaces dressed to form smooth, continuous slopes. In the strong Egyptian sun, the pyramid would not have appeared as the brown, stepped mass familiar today, but as a sharply defined geometric body reflecting pale light across the plateau. Its edges would have been cleaner, its faces visually flatter, and its summit much closer to a true point. What survives now is largely the structural body beneath that polished skin. Measuring the exposed core and treating it as the finished design is like measuring the framing of a building after its walls have been removed. Fragments of the original casing remain near the base, especially where later stone robbers failed to extract them or where the lowest courses were protected by surrounding debris. These remnants are among the most valuable pieces of evidence for reconstructing the pyramid's footprint. Surveyors also study the sockets and prepared bedrock surfaces that once supported casing blocks. In some places, the ancient builders cut into the plateau to create level foundations. In others, they incorporated natural rock into the lower body of the pyramid. The original boundary must therefore be inferred from surviving stones, cut lines, corner positions, foundation trenches, and subtle traces that can be difficult to identify after thousands of years. This is why modern surveys do not simply place a tape measure against the monument. The apparent corners are not always the original corners. The visible base of the core is not necessarily the intended outer base. Even when a casing stone survives, its exposed edge may be damaged. Researchers must decide which surface best preserves the ancient line, then extend that line across long distances where the corresponding stones are gone. A small uncertainty at one corner can alter the calculated length of an entire side. When those reconstructed sides are later used to test mathematical ratios, the initial assumptions become critically important. The summit presents an even greater problem because it has vanished completely. The uppermost courses were removed or collapsed, leaving a flat platform where the final point once stood. The original pyramidion, the capstone that may have crowned the monument, has never been securely identified. The intended height must be reconstructed by projecting the surviving slopes upward until they meet, but the faces do not survive as perfectly uniform planes. Erosion, missing casing, block displacement, and slight variations in construction make the projection less straightforward than it appears. Depending on the measurements used, the reconstructed apex may move slightly, and even a small movement changes the calculated height. The commonly cited original height of roughly 146.6 meters and base side of about 230 meters are reliable approximations, but they should not be mistaken for measurements taken from an intact object. They are reconstructions supported by surviving evidence. The pyramid's present height is lower by several meters, and its exposed sides sit inward from the original casing surface. This difference matters when popular calculations compare the perimeter with the height, or claim that a particular constant is encoded with extraordinary precision. The numbers may appear exact only after damaged dimensions have been replaced with chosen reconstructions. The ground beneath the pyramid adds another layer of complexity. The Giza Plateau is not a perfectly flat slab. It is a natural limestone formation with rises, depressions, fissures, and areas of varying quality. The builders shaped this landscape rather than removing it entirely. In places they cut down higher rock, elsewhere they filled or built over lower zones. A natural mound may remain enclosed within the pyramid's lower courses, reducing the amount of quarried stone required, but complicating any modern attempt to picture the structure as a uniform stack of blocks beginning from a single artificial floor. Achieving a level base across such an enormous area was itself a geometric accomplishment. Water levelling methods have often been proposed, perhaps using channels or trenches filled with water to establish a horizontal reference. Other reconstructions rely on careful sighting with simple instruments, repeated checks, and local adjustments. No complete archaeological evidence proves one universal method. What survives in the record suggests that Egyptian builders possessed several practical techniques for transferring levels and straight lines across construction sites. The mystery lies not in whether they could level ground, but in how they applied those methods efficiently over the full footprint while preserving the intended orientation and dimensions. The four sides also do not form an absolutely perfect square. Modern surveys reveal small differences in length and slight deviations at the corners. These irregularities are tiny relative to the scale of the monument, yet they are important because they expose the reality of construction. The pyramid was not created by an abstract geometric command that forced every block into mathematical perfection. It was made through thousands of measurements, corrections, alignments, and compromises. The remarkable feature is not that error is absent, but that error was contained. This distinction is often lost in descriptions that call the Great Pyramid flawless. It is not flawless. Some core blocks are irregular. Courses vary in height, joints widen and narrow. The central lines of the faces do not always behave exactly as a simplified diagram suggests. There is evidence that certain alignments were adjusted as work progressed. These are not failures. They are traces of an enormous project being managed in real conditions, with tools that depended on human observation and materials that did not always conform to ideal shapes. The pyramid's original appearance may also have included subtle features almost invisible today. Each face appears to have a slight inward depression along its central vertical line, creating an extremely shallow concavity. Under certain lighting conditions, especially when shadows fall obliquely across the faces, the pyramid can seem divided into 8 planes rather than 4. Scholars still debate whether this was a deliberate design feature, a structural consequence of casing placement, or the result of later deformation and stone removal. Because the casing is largely gone, certainty remains difficult. The surrounding complex must also be restored mentally. Khufu's pyramid did not stand alone in an empty desert. It belonged to a planned architectural landscape that included temples, causeways, smaller pyramids, mastaba cemeteries, boat pits, work areas, quarries, and access to ancient waterways. The geometry of the main pyramid was embedded within this broader arrangement. Its orientation shaped nearby structures, while the plateau's geology and the Nile's changing branches influenced transport and construction. The monument's clean form emerged from a landscape crowded with movement, measurement, noise, stone dust, ropes, sledges, ramps, food supplies, administrative records, and repeated human labour. The vanished Aramat branch of the Nile helps restore part of this setting. The pyramid fields were once far more closely connected to navigable water than the modern landscape suggests. Stone, equipment, and provisions could move through channels and harbour facilities before being hauled onto the plateau. The pyramid's geometry therefore depended on geography. Precise dimensions meant little unless enormous quantities of material could arrive in the right order and at a workable pace. Reconstructing Khufu's pyramid is not merely an exercise in replacing missing stones. It means recovering the outer casing, summit, foundation lines, ancient ground levels, transport landscape, and sequence of construction decisions. Every restored dimension carries a degree of uncertainty, but together the surviving traces reveal something more impressive than a mythical perfect object. They reveal a monument whose geometry was imposed upon an uneven natural world, maintained through constant adjustment, and preserved well enough that its original form can still be approached, though never seen whole again. The effort to measure the Great Pyramid begins almost as soon as people start asking what it was meant to be. For ancient visitors, the monument is already old beyond ordinary memory, and its dimensions become part of the fascination surrounding it. Greek and Roman writers attempt to describe its size, but their figures pass through unfamiliar units, copied manuscripts, and uncertain methods. Later travellers pace its base, estimate its height from shadows, lower lines from exposed courses, and compare one side with another while sand, debris, and ruined masonry conceal the original edges. Each generation believes it is approaching the true pyramid, yet each is measuring a different state of preservation with a different idea of what counts as the monument's boundary. This history matters because the numbers attached to the Great Pyramid are not timeless facts discovered all at once. They are the products of surveys, assumptions, instruments, and reconstruction. A side length written to several decimal places may look absolute, but it rests on decisions about which surviving marks belong to the original casing line. A height may appear definitive, though the summit no longer exists. Even a highly precise orientation must be derived from points that have survived unevenly around a structure altered for thousands of years. Early measurements are often ingenious, but they are limited by access and conditions. Sand accumulates around the lower courses. Fallen stone covers parts of the platform. The corners are damaged or hidden. The base is so large that keeping a straight reference line over the full distance is difficult. Heat distorts the air. Uneven terrain interferes with sight lines. Instruments expand and contract. A measuring chain may sag. A rod may not lie perfectly level. Errors that seem tiny over a few meters can grow when repeated across more than 200 meters. The pyramid itself also confuses the surveyor. Its exposed core is not the same as its finished casing. Some blocks project farther than others. The lower platform contains cuttings and sockets that may preserve the original outline more faithfully than the visible masonry above. At the corners, later damage can erase the exact meeting point of two faces. A surveyor must therefore do more than record what is physically present. The surveyor must interpret the remains. By the 19th century, increasingly systematic expeditions begin to replace estimates with triangulation, careful levelling, and repeated observations. Surveyors establish networks of reference points around the monument. They measure angles between stations, compare elevations, and attempt to locate the lost casing lines. Their work produces much more reliable dimensions, but it also reveals why different investigators can reach slightly different answers without either being careless. One may measure the surviving core. another may reconstruct the casing edge, another may give greater weight to foundation sockets. Their figures describe related but not identical geometric objects. Some of the most influential early modern surveys are conducted with extraordinary patience. Researchers clear debris from selected areas, inspect the base course, and record the position of surviving casing stones. They examine each corner separately because no corner survives in precisely the same condition. The result is not a simple square traced directly on the ground. It is a square inferred from fragments, with each fragment carrying its own degree of confidence. As instruments improve, the scale of possible precision changes. Theodolites allow angles to be measured far more accurately than unaided sighting. Steel tapes and calibrated rods replace rough chains. Optical levels help establish elevation differences. Later, electronic distance measurement and total stations combine angle and distance readings with computerized calculation. Satellite positioning can connect local surveys to wider geographic coordinates, while laser scanning records millions of surface points across exposed masonry. Photogrammetry builds three-dimensional models from overlapping images. The pyramid becomes not merely an object to be measured at selected points, but a dense digital landscape. Yet better instruments do not automatically remove uncertainty. A laser can record the location of a damaged stone with extraordinary accuracy, but it cannot decide whether that stone preserves the original design line. Precision of observation is different from certainty of interpretation. Modern surveyors may know exactly where a surviving edge sits, while still debating what that edge once represented. The 2015 footprint survey associated with Glendash illustrates the problem clearly. Rather than treating the visible core as the original base, the work focused on reconstructing the casing lines from surviving evidence around the perimeter. Where casing stones remained, their outer faces offered direct clues. Where they had vanished, sockets and prepared surfaces helped extend the line. The four corners could then be calculated from the intersection of reconstructed sidelines. This approach produced estimates for the original side lengths and revealed very small differences among them. Those differences are central to the pyramid's reputation. The sides are remarkably close in length, especially when compared with the monument's immense scale. But they are not identical. The western side appears slightly longer than the eastern side, and the northern and southern dimensions differ by small amounts depending on the reconstruction used. The precise values matter less than the larger lesson the base is impressively square, yet not mathematically perfect. The corner angles show the same pattern. Each is close to 90 degrees, but small deviations remain. Some errors may reflect ancient setting out, others may arise from the incomplete survival of the casing line. The evidence remains incomplete, and there is no way to return to the plateau on the day the first corner stakes were fixed. What modern measurement offers is not a flawless blueprint, but a range within which the original design can be understood. Orientation is measured in a similarly careful way. Surveyors determine the direction of each reconstructed side relative to true north, not magnetic north, which shifts over time and place. The Great Pyramid's sides deviate from the cardinal directions by only a few minutes of arc. This is a tiny angular error. Across the full side length, however, it produces a measurable lateral displacement. The north side runs slightly away from exact east-west, and the other sides preserve related deviations. These small directional differences have been compared with those of the other major pyramids at Giza. Because the monuments show patterns of slight clockwise or counterclockwise error, researchers have tested whether a shared astronomical method could explain them. Stellar alignment, solar shadow observations, and equinoctial methods have all been proposed. The measurements constrain these hypotheses, but they do not identify one procedure beyond dispute. The history of surveying also reveals a quieter source of confusion: units. Ancient Egyptian builders worked in cubits, palms, and fingers, while later investigators report feet, meters, degrees, ratios, and decimal reconstructions. Converting among these systems can create an illusion of hidden meaning. If the original base was intended as a whole number of royal cubits, slight uncertainty in the cubit's exact practical length affects the reconstructed total. A modern value that seems unusually elegant in meters may have had no significance to the builders, because meters did not exist. The pyramid attracts numerical pattern seeking precisely because modern surveys provide such detailed figures. Once dozens of dimensions are available, they can be compared with astronomical cycles, mathematical constants, geographic coordinates, and proportions drawn from other monuments. Some comparisons are historically plausible. Others emerge only after choosing particular measurements, rounding rules, or unit conversions. The more precisely the pyramid is measured, the easier it becomes to find patterns that may never have been intended. This does not make measurement futile. It makes disciplined measurement essential. The work of surveyors strips away both exaggeration and dismissal. It shows that the pyramid is neither a perfect mathematical crystal nor a roughly improvised heap of stone. It is a carefully controlled structure whose small irregularities preserve the marks of real construction. Across 2 centuries of increasingly accurate surveys, the giant has not become smaller or less mysterious. Instead, the mystery has changed. The question is no longer whether the pyramid is large, square, and closely aligned. Those facts are secure. The deeper problem is how the builders maintained such control while the monument rose beyond the reach of the very reference points that first defined it. Modern instruments can measure the result to millimeters in places, but they cannot yet recover every ancient decision that produced it. The Great Pyramid does not merely occupy the Giza Plateau, it is turned upon it with extraordinary care. Each face looks toward one of the 4 cardinal directions, and the error is so small that it is measured in minutes of arc rather than whole degrees. This precision has become one of the monument's most famous features because orientation is harder than it first appears. North is not marked on the desert floor. East and west are not fixed lines waiting to be followed. The builders had to derive them from the sky, transfer them to the ground, preserve them across more than 200 meters, and then keep the rising mass faithful to those directions, while stone gradually covered the original reference points. The result is often described too simply. Popular accounts say the pyramid points exactly north, as though its orientation were perfect and inexplicable. It is not exact. The sides are slightly rotated from the true cardinal axes, and the deviations are not identical. Yet the errors are very small, especially for a monument constructed around the middle of the 3rd millennium BCE. The achievement does not require supernatural assistance, but it does require careful observation, repetition, and a surveying tradition capable of turning temporary phenomena in the sky into durable lines on stone. Magnetic compasses cannot explain the alignment. Magnetic north differs from true north and shifts over time, and there is no credible evidence that Old Kingdom pyramid builders used compass-based surveying. The most plausible methods depend instead on the regular movements of the sun and stars. Both provide access to the cardinal directions, though neither produces a perfect answer without difficulty. The sun offers the most immediate possibility. A vertical rod planted in level ground casts a shadow that moves during the day, By tracking the tip of that shadow, surveyors can establish an east-west line and derive north-south at a right angle. One common reconstruction uses a circle drawn around the rod. The morning shadow crosses the circle at one point, and the afternoon shadow crosses it again. A line between those points approximates east-west. Repeated observations can reduce error, while longer sighting distances make small deviations easier to detect. The method sounds simple because its principles can be demonstrated with a stick, string, and sunlight. At the scale of the Great Pyramid, however, simplicity becomes demanding. The ground must be level enough for the observations to remain consistent. The rod must stand truly vertical. The shadow edge may be blurred by atmospheric conditions and the finite width of the sun. The morning and afternoon observations must be compared carefully, and seasonal changes affect the geometry of the shadow. A line established in one small area must then be extended across the full building site without bending. A related proposal uses observations near the equinox. When the sun rises close to due east and sets close to due west, Glenn Dash's experimental work has shown that an equinoctial shadow method can produce a slight clockwise rotational error similar in direction to the errors seen in several Egyptian pyramids. This does not prove that Khufu's surveyors used that exact procedure. It demonstrates that ordinary solar observations, handled with discipline, can achieve the required order of precision without invoking lost instruments. The equinox itself would not necessarily have been identified through a modern calendar calculation. Surveyors could observe changes in sunrise, sunset, or shadow positions over successive days and select the point at which those movements crossed an established reference. The process may have involved repeated observations rather than a single ceremonial moment. What survives in the record suggests a culture deeply attentive to solar cycles, temple orientation, agricultural seasons, and the relationship between royal architecture and the ordered cosmos. Stars provide another possible route. The northern sky is especially useful because stars there circle around the celestial pole. Today, Polaris lies close to true north, but in Khufu's time it did not occupy the same convenient position. Earth's rotational axis slowly changes direction through precession, so the location of the celestial pole among the stars shifts over millennia. Old Kingdom observers therefore could not simply sight along the modern North Star. They may instead have watched pairs of circumpolar stars. When two selected stars formed a vertical line, an observer could use a plumb line or sighting instrument to mark the direction of the celestial pole. Repeated observations over multiple nights might refine the line. Some researchers have compared the small orientation errors of different pyramids with the changing positions of candidate star pairs, arguing that precession could explain why monuments built at different times rotate slightly away from true north. The idea is elegant, but no single stellar pair or observing procedure has won universal acceptance. Chronology, atmospheric refraction, the exact dates of construction, and the practical design of the instrument all affect the result. Scholars still debate whether stellar methods, solar methods, or combinations of both best explain the evidence. A method that works mathematically must also be plausible on a busy construction site and must produce the actual pattern of errors preserved in the masonry. The ancient Egyptians possessed tools suitable for careful sighting. A merket, known from later periods, could be used with a plumb line to establish vertical references and observe stars. A bay, or sighting instrument, may have helped define lines between fixed points. Ropes, rods, stakes, and right-angle constructions could transfer those lines across the ground. The absence of a surviving Old Kingdom surveying kit does not mean the techniques were unknown. It means that much of the procedure must be reconstructed from later instruments, tomb scenes, texts, architectural results, and practical experiment. Once north had been established, the other directions could be created geometrically. East-west lies perpendicular to north-south. But constructing an accurate right angle over a vast area is not trivial. The builders may have used ropes to create intersecting arcs, producing perpendicular lines through simple geometry. They could also have checked diagonals across the planned square. If both diagonals were equal and cross correctly, the layout was closer to square, yet every rope stretches, every stake has width, and every mark occupies physical space. The process likely depended on repeated checking rather than one perfect operation. This repetition may be the least dramatic and most important part of the answer. The Great Pyramid's alignment is sometimes treated as though a single brilliant observation fixed the monument forever. More likely, the builders established a direction, checked it with another observation, transferred it, tested the resulting square, and corrected the lines before construction advanced too far. Precision at Giza may have emerged not from one impossible measurement, but from a culture of redundancy. A lesser-known difficulty appears when the reference lines begin to disappear beneath masonry. At the start, surveyors can work across the open foundation. Once the lower courses are laid, the original axes may be partly hidden. The builders then need secondary marks outside the footprint, sighting stations on the plateau, or reference lines preserved within passages and central axes. They must ensure that each rising face remains parallel to the intended baseline. A small rotational drift in the lower courses would become increasingly difficult to correct higher up. The descending passage may preserve part of this relationship between external orientation and internal planning. It runs roughly north-south and slopes downward into the bedrock from the northern face. Its alignment suggests that internal corridors were tied to the broader geometric scheme rather than inserted independently. The builders were not merely orienting a shell, they were coordinating external faces, internal passages, chambers, and the natural rock beneath them. The meaning of the cardinal alignment also reaches beyond surveying. Egyptian kingship was connected to cosmic order, solar movement, and the enduring northern stars. The north was associated with the imperishable stars that never seemed to set, while east and west framed sunrise, sunset, birth, death, and renewal. The Great Pyramid's orientation therefore served both practical and symbolic purposes. Geometry was not separate from religion. To align the monument with the world was also to place the king within an ordered universe. No surviving text explains the full ceremony or method used for Khufu's pyramid. The evidence remains incomplete. Solar observations can account for much of the precision. Stellar observations remain plausible. Combined procedures may have offered independent checks. What can be said with confidence is that the alignment was achievable through ancient surveying and astronomy, though not casually and not without accumulated expertise. The four sides facing the world are therefore neither proof of impossible knowledge nor a trivial accident. They are evidence of disciplined observation translated into architecture. The pyramid stands slightly imperfectly upon the cardinal grid, and that small imperfection is valuable. It shows that human beings made the lines, tested them, and came remarkably close to the directions they sought. The wonder lies not in errorlessness, but in how little error survived. Once the pyramid square has been fixed upon the plateau, another problem begins immediately. A base can be laid out on level ground, checked from corner to corner, and compared against the sky. A slope is harder. It must remain consistent as the monument rises. Course after course, While the working surface grows smaller, the original baseline recedes below, and every slight mistake threatens to move the four faces away from the point where they are meant to meet. The Great Pyramid's slope is often given as an angle of a little more than 51 degrees. That is the modern way of expressing it. Khufu's builders almost certainly did not think in decimal degrees or modern trigonometric functions. They used a practical Egyptian system known as the seked, a method that described the horizontal movement of a sloping face for a fixed vertical rise. Rather than asking for an angle in degrees, a builder could ask how many palms the face moved inward for every royal cubit it rose. A royal cubit was divided into 7 palms, and each palm into 4 fingers. This made the seked a convenient working ratio. A steep pyramid had a smaller horizontal run for each cubit of height. A shallower pyramid had a larger one. The method appears in surviving mathematical texts from later periods, where problems asked scribes to calculate the slope of pyramids from height and base dimensions. The surviving documents are younger than the Great Pyramid, so they cannot serve as direct construction records from Khufu's reign. Even so, they preserve a mathematical tradition that likely developed from much earlier architectural practice. For the Great Pyramid, a frequently proposed seked is 5 palms and 2 fingers for every cubit of vertical rise. In modern terms, that means the face moves inward by 5.5 palms while rising 7 palms. This produces a ratio close to the reconstructed slope of the monument. The numbers are simple enough to be used repeatedly, yet precise enough to generate the pyramid's distinctive form. This is a crucial point because the visible mathematical sophistication of the Great Pyramid does not require its builders to possess modern formulas in modern notation. A ratio can produce the same geometry as an angle, without ever being expressed as an angle. Workers checking a face do not need to calculate a tangent. They need a reliable measuring rule, a plumb reference, and a way to verify that each course retreats by the correct amount as it rises. The seked therefore turns an abstract slope into a sequence of physical operations. A vertical measure can be established with a plumb line. A horizontal setback can be marked with a rod or rope. Over several courses, the accumulated retreat can be checked against the expected value. If one section drifts outward or inward, the next course can compensate slightly before the mistake becomes too large. Precision emerges through repetition and correction, rather than through one calculation made at the beginning and never revisited. The challenge is that masonry does not behave like a drawn line. Core blocks are irregular, courses vary in height. The exposed outer face during construction may not yet be the final casing surface. A block that is slightly too large cannot always be trimmed instantly without affecting the rhythm of work. The builders must coordinate rough core masonry with the more exact casing line that ultimately defines the slope. This suggests that the true geometric surface was controlled by selected reference points, guidelines, or finished casing stones rather than by expecting every internal block to follow an ideal plane. One possible method involves measuring from the edges of completed lower courses. Another uses plumb lines suspended from temporary frames or sighting points. Builders may have stretched chords along faces or established vertical profiles at corners and central points. Corner casing stones, carefully shaped and set, could define the edges while intermediate stones filled the plane between them. The exact procedure remains uncertain, but the surviving monument shows that some combination of local measurement and broader alignment kept the faces from wandering far from the intended slope. The corners were especially important. Each corner had to rise along a straight line while 2 adjacent faces retreated inward at matching rates. If one corner moved too quickly toward the center, one face would become steeper and the neighboring face distorted. If it moved too slowly, the opposite problem appeared. Checking the corner lines may have offered a powerful way to control the whole form, since a pyramid's edges make deviations more visible than broad, rough surfaces. The centre of each face may also have served as a reference. This slight concavity visible on the Great Pyramid's faces complicates the idea that each side was intended as one perfectly flat plane. Some researchers argue that the casing may have been set with a shallow inward break along the middle, creating two subtle planes per face. Others see the effect as structural settlement, later damage, or the consequence of casing removal. If the concavity was intentional, then the builders were managing not one slope per face but two closely related planes. The evidence remains incomplete, and the lost casing prevents a final answer. This seked also helps explain why several Egyptian pyramids have noticeably different shapes. The bent pyramid changes slope partway up, creating its famous broken profile. The red pyramid rises more gently. Later pyramids use other proportions. These variations show that Egyptian builders were not trapped by one sacred angle. They experimented, adjusted, and selected slopes with different structural, aesthetic, and practical consequences. The bent pyramid is particularly revealing because its change of angle preserves the memory of correction on a monumental scale. The lower section begins steeply, but the upper section becomes shallower. Scholars debate the precise reasons, including structural instability, cracking, time pressure, or lessons learned during construction. Whatever the combination, the monument demonstrates that pyramid geometry could be revised in response to real conditions. Khufu's builders inherited not only mathematical knowledge but generations of costly architectural experience. By the time the Great Pyramid rose at Giza, the chosen slope balanced several demands. A steeper pyramid reaches greater height from a given base, but places different stresses on the masonry, and requires more difficult lifting near the upper levels. A shallower pyramid spreads farther across the ground and consumes more space. The chosen seked influences the monument's height, volume, face area, stone requirements, ramp geometry, and rate at which the working platform shrinks. A single proportion echoes through the entire construction system. This makes the slope more than an aesthetic decision. It is tied to logistics. Each upward course requires fewer blocks than the one below, but those blocks must be lifted higher and placed in a more confined area. The inward retreat affects how ramps connect to the structure, how workers move around the faces, and how corners remain accessible. The geometry determines the changing shape of the workplace. A surprising feature of the seked is how easily it can produce ratios that later observers interpret through other mathematical systems. When the pyramid's height, half base, face length, and perimeter are compared, relationships appear that resemble famous constants. Some may be intentional consequences of the chosen slope. Others may be byproducts of the ratio itself. The danger begins when modern interpreters reverse the process and assume that because a constant can be extracted from the dimensions, that constant must have been the original design goal. The ancient builder may have needed nothing more mysterious than a chosen run and rise. 5 palms and 2 fingers is practical, repeatable, and compatible with the reconstructed monument. It can create geometry that looks sophisticated in modern notation because it is sophisticated, though expressed in a different mathematical language. No surviving plan states that this exact seked governed every face of Khufu's pyramid. Small variations in reconstructed slope remain, and the missing casing prevents perfect verification. Scholars still debate whether the intended dimensions were fixed primarily by height, base length, slope, whole cubit counts, or some combination of them. A project of this scale may also have involved adjustment as construction advanced. What survives suggests a system in which geometry was not separated from craft. The slope lived in ropes, palms, fingers, plumb lines, dressed stones, and repeated checks. It was carried upward by people who understood proportion through practice. The Great Pyramid's angle does not require an impossible mathematics. It reveals something more grounded and perhaps more impressive, a simple ratio maintained across a structure so vast that even simplicity became an extraordinary feat. The seked does more than determine the Great Pyramid's slope. Once that rise and run ratio is extended across the full monument, another relationship appears, one that has fascinated mathematicians, surveyors, mystics, and popular writers for generations. If the reconstructed height is compared with the total perimeter of the square base, the numbers come close to a circle. More specifically, the perimeter is approximately equal to the circumference of a circle whose radius is the pyramid's height. In modern notation, the relationship can be written as perimeter divided by twice the height, producing a value close to pi. This is the moment when a practical construction ratio begins to look like a hidden mathematical message. The resemblance is close enough to be striking. A square monument appears to contain the geometry of a circle. Stone faces rising from a four-sided base seem to encode a constant that links diameter and circumference. From there, the claim often grows the builders must have known pi to exceptional precision and deliberately built it into the pyramid. The difficulty is not that the relationship's imaginary. It is real enough to measure. The difficulty is deciding what it means. Using commonly reconstructed dimensions, the Great Pyramid's original base side is close to 230.3 meters and its height close to 146.6 meters. 4 times the base gives a perimeter of roughly 921 meters. Twice the height gives about 293 meters. Dividing one by the other produces a value near 3.14. The exact result changes slightly depending on which reconstruction is used, how the missing casing is restored, and what original height is assumed. Yet the broad relationship survives most reasonable estimates. That durability gives the pi interpretation its power. It is not a fragile coincidence that vanishes with the first small adjustment. At the same time, the ratio does not prove that the builders began with pi as an abstract constant and designed outward from it. The same geometry can emerge from the seked already considered. A slope of 5 palms and 2 fingers for every cubit of rise produces proportions that naturally bring the perimeter to height relationship close to 2 pi. The circle-like ratio may be a consequence of the chosen slope rather than the reason for choosing it. This distinction between cause and consequence is central. A modern observer can calculate pi from the finished form. An ancient builder may have thought only in whole cubits, palms, and fingers. The two descriptions can refer to the same shape without implying the same design process. Geometry allows different mathematical languages to converge on identical results. Ancient Egyptian mathematics did include practical approximations for circles. The Rind mathematical papyrus, copied long after Khufu's reign from an earlier tradition, contains a method for estimating the area of a circle. Its rule effectively gives a value for pi that is reasonably accurate for calculation, though not identical to the ratio suggested by the Great Pyramid. This proves that Egyptian scribes could solve circular problems with effective numerical procedures. It does not prove that Khufu's architects used a formal concept of pi in designing the monument. The chronology matters. A mathematical papyrus copied in the 2nd millennium BCE cannot simply be placed in the hands of 4th dynasty builders. It may preserve older knowledge, but the chain of transmission is incomplete. The safest conclusion is that Egyptian mathematics was capable of handling circles, slopes, areas, and volumes in practical ways. The evidence does not establish a theoretical system equivalent to later Greek geometry. There's also a problem hidden inside the word precision. Popular accounts sometimes compare a highly rounded modern value of pi with pyramid dimensions reported to many decimal places. This gives the impression of near-perfect correspondence, but the original pyramid is damaged, and its intended dimensions are reconstructed rather than directly observed. A few centimeters added to or subtracted from a side, or a small change in the projected apex, alters the ratio. The builders themselves worked with physical stones, not infinitely thin mathematical lines. A numerical match should therefore be judged within the uncertainty of the monument. If the reconstructed dimensions support a ratio close to pi, that is meaningful. If a claim depends on selecting one disputed height, one preferred side length, and a particular rounding scheme to reach an impressive string of digits, the interpretation becomes much weaker. No single explanation fully accounts for why some measurements seem so elegant while others resist the same treatment. The choice of units can further amplify the mystery. Measurements expressed in meters may produce attractive decimals, but meters are modern. Ancient builders likely planned in royal cubits. If the base was intended as approximately 440 cubits, and the height is approximately 280 cubits, the ratio becomes especially clear. 4 times 440 gives 1,760. Twice 280 gives 560. The result: 1,760 divided by 560 is 22 divided by 7, or about 3.142857. This is one of the lesser-known reasons the pi debate remains so persistent. The fraction 22/7 is a close approximation to pi, and the pyramid's commonly reconstructed cubit dimensions reproduce it naturally. Yet 22/7 is also exactly what follows from the proposed seked. Half the base is 220 cubits. Dividing that by a height of 280 cubits gives 11/14 the same horizontal to vertical relationship represented by 5.5 palms to 7 palms. The apparently circular constant and the practical slope ratio are two views of the same arithmetic. That means the builders could have arrived at the geometry without asking for a circle at all. They may have selected a convenient seked and whole number dimensions, after which the pi-like relationship emerged automatically. They may also have appreciated the resulting connection between square and circle, especially in a culture where architecture, cosmic order, and symbolic form were intertwined. The evidence cannot cleanly separate these possibilities. The symbolism of a circle would not have been meaningless in Egypt. The sun's path, celestial cycles, horizons, and concepts of eternity carried powerful religious significance. The pyramid itself participates in a visual language of ascent and solar radiance. It is tempting to imagine that a circular proportion was intentionally embedded within the square base, but symbolic plausibility is not proof of numerical intent. Any large geometric structure offers many measurable quantities side length, diagonal, height, slant height, perimeter, area, volume, chamber dimensions, passage angles, and distances between internal points. Once enough quantities are compared, some will approximate familiar constants. This does not mean all patterns are meaningless. It means each claim must be tied to evidence for ancient units, methods, and plausible construction choices. The pi relationship is stronger than many fringe numerical claims because it arises from the basic exterior dimensions and from a historically plausible slope system. It cannot be dismissed as random number play, but neither can it be promoted confidently as proof that the pyramid was designed as a monumental textbook of advanced constants. What survives in the record suggests a more subtle answer. The Great Pyramid's proportions are compatible with a practical seked whole number cubit dimensions and a perimeter to height ratio close to pi. These facts can all be true at once. The uncertainty lies in which relationship was primary in the minds of the designers. The stone does not announce its equation, it preserves a form. Modern mathematics can describe that form with pi, while ancient mathematics may have described it through palms and cubits. Between those languages stands the pyramid itself, silent and exact enough to invite interpretation, yet incomplete enough to prevent certainty. Its numbers add up. What remains unresolved is what the builders intended those numbers to say. The same proportions that produce a pi-like relationship also generate another celebrated number. When the Great Pyramid's reconstructed dimensions are compared in a different way, the golden ratio seems to appear. The slant height of a face, measured from the midpoint of the base to the summit, stands in a relationship to half the base that comes close to phi, approximately 1.618. Once again, an apparently simple monument seems to contain a mathematical constant later associated with geometry, art, growth patterns, and ideal proportion. This has encouraged one of the most persistent claims about the pyramid, that its architects deliberately encoded the golden ratio centuries before Greek mathematicians described related geometric relationships. In its strongest form, the claim presents the monument as proof of a lost mathematical science. In a more cautious version, it suggests that Egyptian builders discovered an especially pleasing proportion through practical design, even if they did not express it using the later language of Beg. The measurements do produce a close resemblance. If the original height is taken as about 280 royal cubits and half the base as about 220 cubits, the slant height follows from the right triangle formed by those two dimensions. Using modern calculation, that slant height is a little more than 356 cubits. Dividing it by 220 gives a result near 1.618. The match is close enough to feel intentional, especially when presented beside diagrams of golden rectangles and spirals. Yet the golden ratio claim faces the same problem as the pi claim, only more sharply. The proportion may emerge automatically from the chosen slope. Once the height and half base are fixed at 280 and 220 cubits, the slant height is no longer an independent design choice. It is determined by geometry. A pyramid designed with the proposed seked will produce both the pi-like perimeter relationship and the phi-like slant relationship, because those ratios are mathematically connected. This is why several famous constants can seem to occupy the same monument without requiring several separate design instructions. One practical ratio can generate a family of related measurements. A builder chooses how far the face retreats for each unit of rise. From that decision come the angle, final height, slant height, perimeter to height relationship, face area, and other proportions. Modern observers can then isolate each result and give it a different mathematical name. The golden ratio itself is often surrounded by more mystique than its historical evidence supports. It appears naturally in certain geometric constructions, particularly when a line is divided so that the whole relates to the larger part as the larger part relates to the smaller. Later mathematicians study this relationship explicitly. In modern culture, Phi is often credited with governing everything from temples and paintings to shells, faces, galaxies, and financial markets. Many of these claims are exaggerated, retrofitted, or based on flexible measurement. The Great Pyramid is especially vulnerable to this treatment because its original edges are missing. A researcher can choose among reconstructed heights, base lengths, casing lines, slant measurements, or face apothegms. Slight adjustments may improve or weaken the match. If the monument is first assumed to contain phi dimensions, can be selected that bring the calculation closer to the expected value. That is not the same as independently discovering the ratio from archaeological evidence. The problem becomes clearer when the design process is imagined from the builder's perspective. To deliberately construct the golden ratio, the architects would need to prioritize a relationship between the slant height and half the base, or an equivalent geometric construction. But the slant height is awkward to measure directly during building. It lies along the inclined outer face, which changes constantly as courses rise and may be interrupted by ramps, scaffolding, casing operations, and rough core masonry. Height, base length, and horizontal setback are much easier to control with cubit rods, levels, plumb lines, and the seked. That does not make deliberate phi impossible. A geometric relationship can be established through diagrams or derived from other proportions, but no surviving Old Kingdom text states that the Great Pyramid was designed around a division equivalent to the golden ratio. No Egyptian name for phi is known from the period. No construction manual identifies it as a sacred or architectural constant. The evidence remains incomplete. An absence of documentation is not absolute proof of absence, but the burden of demonstration lies with the stronger claim. A more plausible interpretation begins with whole number dimensions. A base of roughly 440 cubits and a height of roughly 280 cubits create a clear, manageable plan. Half the base is 220 cubits, and the rise-to-run relationship matches the proposed seked. These numbers fit the Egyptian measuring system directly. The golden ratio appears only after the slant height is calculated through a modern application of the Pythagorean relationship. This introduces another historical caution. Builders can create right triangles and work with diagonal distances without possessing later Greek proofs or algebraic notation. Practical geometry often precedes formal theory. Egyptian rope stretchers, surveyors, and architects could compare sides, diagonals, and slopes through physical methods. It is therefore unnecessary to deny them geometric sophistication simply because the language of phi belongs to a later mathematical tradition. The distinction is between possessing a relationship and treating it as a universal constant. A carpenter can produce a pleasing rectangle through repeated proportional division without naming the golden ratio. A mason can create a triangle whose sides later yield phi without recognizing it as an abstract number. Ancient design may contain relationships that modern mathematics describes more explicitly, but description should not automatically be mistaken for intention. The pyramid's proportions may also have been selected for visual and structural reasons. A face angle near 51.5 degrees gives the monument a steep, commanding profile, while keeping the base broad enough to distribute its mass. The slope may have seemed visually appropriate within the evolving tradition of pyramid building. It may have balanced height, stability, available space, labor demands, and casing geometry. None of these practical considerations requires a search for ideal constants. Comparison with other Egyptian pyramids makes the issue more revealing. Different monuments use different slopes, and not all reproduce the golden ratio closely. If phi were a fixed sacred requirement, one might expect more consistency. Instead, the sequence from the step pyramid through Sneferu's monuments and later royal pyramids shows experimentation. Some pyramids are steeper, some shallower, some altered during construction, and some built with less precision. The Great Pyramid's proportion belongs to a tradition of choices rather than standing outside it as a mathematical anomaly. There is still room for intentional elegance. Khufu's architects may have selected a seked partly because the resulting proportions were visually satisfying. They may have inherited rules that encoded generations of observation about stability and appearance. A ratio does not need to be identified as phi to be chosen deliberately. The builders could have understood that certain relationships produced harmonious forms without separating aesthetics from engineering. This possibility is more grounded than the claim that the pyramid was built to preserve secret mathematical knowledge for the distant future. Egyptian royal monuments were designed for their own cultural world. Their geometry served construction, ritual, kingship, landscape, and cosmic order. It was not necessary for the architects to anticipate modern number theory in order to create a form later generations would find mathematically rich. The golden ratio problem, therefore, does not end with a simple yes or no. The proportion is genuinely present within commonly reconstructed dimensions. It may arise as an unavoidable consequence of the selected seked. It may also have contributed to the monument's visual success, and perhaps to the designer's preference for that slope. What cannot be shown securely is that phi itself, as an abstract and deliberately encoded constant, governed the plan. The Great Pyramid continues to invite this kind of projection because it seems too ordered to be accidental and too damaged to answer every question. Modern minds bring circles, spirals, constants, and ideal rectangles to its faces. Some of those comparisons reveal real geometric relationships. Others reveal the human tendency to find intention wherever numbers align. The deeper lesson is not that every elegant ratio is false, but that elegance alone is not evidence. A monument can contain pi and phi as mathematical consequences, while having been designed through cubits, palms, fingers, slopes, and practical checks. The numbers still lead somewhere. They simply may lead back to Egyptian craft rather than forward to a hidden universal code. The numbers become more revealing when the pyramid is no longer treated as a perfect diagram. On paper, the Great Pyramid is a square base beneath four identical triangular faces. On the plateau, that ideal form breaks into small but persistent irregularities. The four sides are not exactly the same length. The corners do not form four mathematically perfect right angles. The faces may not even be perfectly flat. Running down the center of each face is a subtle inward depression, so slight that it can disappear in ordinary light and suddenly emerge when shadows strike at the right angle. A monument usually imagined as four-sided may, under certain conditions, reveal 8 shallow planes. These irregularities matter because they challenge the popular image of the pyramid as a flawless geometric object. If the structure were perfect in the absolute sense often claimed, each side would match, every corner would close at precisely 90 degrees, and each face would form one uninterrupted plane from edge to edge. The real monument is more complicated. Its precision is remarkable, but it is the precision of an immense human construction, not the perfection of an abstract mathematical solid. Modern footprint surveys show small differences among the reconstructed base lengths. The exact figures depend on which casing remnants, sockets, and corner traces are accepted, but the general result remains stable. The sides are extremely close, yet not identical. Across a base more than 230 meters wide, discrepancies of several centimeters are astonishingly small. At the same time, they matter when ratios are calculated to many decimal places. A claim that the builders encoded a constant with near-perfect accuracy may weaken when the eastern side is used instead of the western, or when an average replaces a preferred measurement. The corner angles reveal the same pattern. Each is close to a right angle, but slight deviations remain. These can arise from several stages of work. The initial layout may have contained tiny errors. Reference lines may have shifted during foundation preparation. Casing stones may have been set with local corrections. Later damage may have erased the true corner and forced surveyors to reconstruct it from incomplete evidence. No single explanation fully accounts for every difference, and the surviving footprint cannot always separate ancient irregularity from modern uncertainty. What is striking is how well the builders prevented those small discrepancies from multiplying. A base that begins out of square creates problems higher up. If opposite sides differ too much, the corners will not retreat toward one common apex at the same rate. One face may need a different slope, or the upper courses may require increasingly awkward adjustments. The Great Pyramid does not display a dramatic geometric collapse of that kind. Whatever errors existed at ground level were kept within limits, and the rising structure was corrected well enough to preserve a coherent summit line. This suggests that the builders did not rely on a single initial measurement. They likely checked diagonals, compared side lengths, monitored corner positions, and adjusted local masonry as the work advanced. A pyramid of this scale cannot be governed by theory alone. It must be watched. The geometry is maintained by repeated acts of comparison, and the surviving irregularities may record where those comparisons led to compromise. The faces present an even stranger problem. Under ordinary daylight, each appears broadly flat, yet aerial photography and oblique illumination have revealed a faint vertical hollow running down the middle of the sides. When the sun is low and shadows divide the surface, the Great Pyramid can appear to have 8 faces rather than 4, each main side split into 2 shallow planes that angle slightly inward toward the centre. This effect is subtle. It is not a dramatic fold. The depression amounts to only a small inward displacement across an enormous width. Because most of the original casing is missing, the exposed core exaggerates some irregularities while concealing others. The question is whether the concavity belonged to the finished design, to the underlying masonry, or to later deformation. One interpretation is that the inward bend was deliberate. A slightly concave face could help the casing appear visually straighter from a distance by compensating for optical effects. It might also improve the stability of the outer skin by directing casing blocks toward the central axis of each face. Some have suggested that the depression served as a surveying aid, dividing each broadside into 2 more manageable planes. If so, the builders were not constructing 4 simple triangles but 8 subtly coordinated surfaces. Another possibility is structural. The centre of a broad face may settle or compress differently from the corners. The outer masonry could have shifted under its own immense weight over centuries. Earthquakes, thermal expansion, weathering, and the removal of casing stones may have altered the visible planes. Once the smooth outer shell was stripped away, the rough core beneath may have exposed construction patterns never meant to define the final appearance. Stone robbing is especially important. Casing removal did not occur evenly. Blocks were extracted where they were accessible and valuable, leaving jagged surfaces and local scars. The lowest courses suffered from quarrying, rebuilding, and later activity around the plateau. A shallow depression visible today might partly reflect how the casing was laid, but it might also reflect how it was dismantled. The evidence remains incomplete because the surface needed to test the original design has mostly vanished. The concavity also complicates the measurement of slope. If each face is subtly divided, then there is no single perfect plane from one corner to the other. Measurements taken near the center may differ slightly from those taken closer to the edges. Reconstructing the original apex from surviving face angles becomes less straightforward, and ratios based on one averaged slope may smooth away real variation. This does not mean the monument was geometrically confused. On the contrary, controlled concavity may indicate a more sophisticated design than a flat-faced model suggests. Ancient builders understood that large structures behave differently from small drawings. Surfaces that appear straight nearby can bow visually across great distances. Edges dominate perception, and light can reveal or conceal irregularities. The final form may have been shaped not only by numerical ratios but by how the pyramid was meant to be seen. There is also a practical advantage in dividing a face conceptually. A side more than 200 meters wide is difficult to control from corner to corner. Establishing a central axis gives surveyors another reference line. Workers can compare the two halves as they rise, and a slight central indentation might emerge from such a method, even if it was not the primary visual goal. The irregularity of the core blocks reinforces this impression of controlled imperfection. Some courses are relatively uniform, others vary in block size and joint width. The outer casing would have concealed much of this roughness, creating a clean geometric skin over a more flexible interior. Precision may have been concentrated where it mattered most: baselines, corners, casing planes, passages, chambers, and principal axes. The core could tolerate more variation as long as the overall mass and outer geometry remained stable. The unequal sides and hidden concavities therefore do not diminish the Great Pyramid. They rescue it from myth and return it to engineering. The monument is extraordinary not because it escaped all error, but because it controlled error across a scale where small deviations should have become destructive. Its faces are almost flat, its sides are almost equal, its corners are almost square, and that repeated almost is where the human story survives. The pyramid's geometry becomes more impressive when its imperfections are seen, because those imperfections reveal the decisions, corrections, and limits that made the monument possible. The pyramid's exterior offers the comfort of a recognizable shape. 4 faces rise from a square base, each retreating toward a missing point. Inside, that clarity disappears. The monument becomes a 3-dimensional problem of passages, chambers, shafts, masonry masses, hidden voids, and changing elevations. Some spaces are cut into the bedrock beneath the pyramid. Others are built inside the rising body. Several do not align neatly with the visual symmetry of the exterior. The result is not a simple hollow monument, but an architectural system whose internal geometry still resists explanation. The descending passage begins on the northern face and drives downward at a steady angle through masonry and then into the plateau itself. It is narrow, severe, and remarkably straight over a long distance. Its builders had to establish the line before much of the pyramid above existed, then preserve that angle as the passage crossed from constructed stone into natural rock. Even this first corridor reveals how closely the interior was tied to the external orientation. It runs broadly along the north-south axis, binding the invisible route beneath the pyramid to the cardinal order fixed at the surface. Far below, the passage reaches the unfinished subterranean chamber. This space is rougher than the chambers above, cut deeply into the bedrock and left in a state that has encouraged centuries of speculation. It may represent an abandoned burial plan, an early construction stage, or part of a sequence of design changes. Its floor is uneven, and a pit descends into it, while another short passage extends away without resolving its purpose. What survives in the record suggests that the builders were willing to alter the internal scheme, while the broader external form remained stable. Above the descending route, the ascending passage branches upward through the masonry. The builders needed to preserve a downward corridor while creating a second route that climbed away from it, all within a mass of stone that would eventually bear enormous weight. The lower end of the ascending passage was concealed behind blocking stones, transforming geometry into security. A corridor was not merely a line through the pyramid, it could be closed, disguised, or made to disappear within the architecture. The ascending passage leads toward the Grand Gallery, an extraordinary space inside the monument. It rises steeply through a tall, narrow corridor, whose walls step inward in corbelled layers. Each higher course projects slightly over the one below, reducing the span near the ceiling. The gallery does not behave like a simple rectangular tunnel. Its cross-section changes with height, distributing masonry while creating a soaring interior after the confined passage below. The Grand Gallery has inspired competing explanations because its scale seems greater than movement alone required. It may have served as a route for transporting large granite blocks toward the king's chamber. Its side ramps, slots, and architectural details may have supported scaffolding, closing systems, or other construction operations. A recent hypothesis proposes that parts of the gallery and connected passages could have participated in counterweight arrangements used during building. That model is intriguing, but it remains disputed and should not be mistaken for archaeological consensus. No single explanation fully accounts for every feature. At the lower end of the Grand Gallery, a horizontal corridor leads toward the chamber traditionally called the Queen's Chamber. The name is misleading. There is no secure evidence that a queen was intended to be buried there. The chamber sits close to the pyramid's central axis and has a pointed roof. Its position has often been used to argue that the internal design changed during construction, perhaps shifting from a lower burial chamber to the higher king's chamber. Yet the room could also have held a symbolic function, or belong to a plan that was never completed as intended. Scholars still debate its purpose. From the Queen's chamber, narrow shafts extend into the surrounding masonry. For a long time, these were casually called ventilation shafts, but they do not open into the chamber in a simple practical way, and their routes are too deliberate to be explained by airflow alone. Their changing angles, blocked ends, and symbolic orientations have encouraged interpretations involving stars, ritual pathways, or construction needs. Robotic investigations have revealed blocking slabs with fittings and further spaces beyond. The geometry continues inward, but certainty does not. Higher in the monument, the Grand Gallery narrows toward the antechamber and the king's chamber. Here, the material changes dramatically. Massive granite blocks from Aswan form the chamber walls, floor, and ceiling. Their transport was a major logistical undertaking, but their placement inside a structure already rising high above the plateau created a geometric and structural challenge. The chamber had to remain aligned, level, and correctly positioned while the pyramid continued to close around it. The king's chamber is often treated as the final destination of the internal plan, yet the architecture continues above its visible ceiling. A sequence of relieving chambers, capped by enormous granite beams and finally a pitched limestone roof, rises through the masonry. These spaces redistribute weight away from the chamber below, though their exact structural behavior remains under study. Recent ultrasonic investigation of the lower wall blocks adds another layer by examining hidden block thicknesses, rear surfaces, joints, and internal reflections. The visible room is only the inner face of a much larger stone assembly. This makes the king's chamber less like a box placed inside the pyramid and more like the center of a managed load system. The walls, ceiling beams, relieving spaces, and surrounding masonry work together. Their geometry matters because a chamber beneath millions of tons of stone survives only if forces are redirected through the structure. Two narrow shafts rise from the king's chamber toward the exterior. Unlike those associated with the queen's chamber, these reach the pyramid's outer faces. Their angles differ, and they do not simply run straight toward the nearest surface. They may have served ritual functions connected with the king's celestial destiny, practical functions during construction, ventilation, or several purposes at different times. Their careful routing shows that the builders coordinated hidden channels with the changing exterior slope. The internal plan is therefore a network of intersecting geometries. The exterior is governed by square, slope, and cardinal direction. The interior adds inclined lines, horizontal corridors, vertical offsets, corbelled sections, chamber volumes, shaft angles, and structural spaces above ceilings. Some elements align with the pyramid's center, others sit slightly north or south of it. Some were cut before the superstructure rose, others had to be built course by course as the mass climbed around them. This coordination required a sequence of control points. Surveyors needed to know where a passage would emerge many meters above its starting point. Builders had to preserve empty space while laying thousands of blocks around it. Granite beams had to arrive before the courses above made access impossible. Shafts had to maintain their direction even as ramps, work platforms, and casing operations changed around them. Modern diagrams make this seem clean because they reduce the pyramid to lines and labels. The construction site was constantly changing. A passage existed first as a measured intention, then as an open corridor, then as a space enclosed by stone. Once sealed, it became invisible from outside. Every successful internal line represents a calculation completed before later masonry erased the evidence of how it was set out. The Great Pyramid's interior does not resolve the mystery of its geometry. It deepens it. The exterior can be surveyed from the plateau, but the interior must be reconstructed from confined passages, hidden masonry, and non-destructive scans. What appears from outside as a single solid mountain contains a second architecture folded through it, extending beneath the base, rising through the core, and still revealing spaces earlier generations never suspected were there. The deeper the Great Pyramid is studied, the more its precision separates into two different realities. One is the ideal geometry preserved in its overall form, the cardinal alignment, the nearly square base, the stable slope, the passages maintaining long straight courses, and the chambers placed within a tightly controlled three-dimensional plan. The other is the physical structure visible at close-range uneven blocks, varying course heights, irregular joints, local corrections, rough core masonry, damaged surfaces, and places where the stone refuses to behave like a perfect drawing. Both realities are true. The pyramid is highly precise, but it is not uniformly precise everywhere. This distinction is essential because the monument's reputation often depends on measurements taken from its best controlled features and then applied to the entire mass. The outer casing lines may have been set with extraordinary care, but many interior core blocks were placed with much wider tolerances. The king's chamber contains granite work of exceptional refinement, while nearby masonry can appear far rougher. Passages maintain impressive alignment, yet the courses surrounding them may vary considerably in shape and fit. Precision was concentrated where geometry, load, visibility, ritual importance, or access demanded it. The pyramid was not built from millions of identical stones cut to machine-like standards. Its blocks differ enormously in size and quality. lower courses contain some very large pieces, while many higher courses use smaller units. Quarry conditions, transport constraints, placement height, and structural role all influence the choice of stone. Some blocks were shaped closely before placement, others were fitted more roughly and adjusted with packing material, smaller fragments, or mortar. The finished casing concealed much of this internal irregularity behind a smooth limestone surface. This method is not evidence of poor construction. It is evidence of efficient construction. A monument of this size does not require every hidden stone to have the same finish as a visible chamber wall. Labour spent dressing an internal core block to unnecessary perfection would slow the project without improving the final geometry. The builders appear to have understood where exactness mattered and where mass, stability, and speed mattered more. The horizontal courses reveal this changing standard. From a distance they look regular, but their heights are not constant from base to summit. Some courses are noticeably taller than those above or below. The pattern may reflect the natural thickness of quarry beds, the availability of particular stone sizes, or deliberate changes in construction rhythm. Taller blocks are common in important lower levels, where the monument bears greater weight, but abrupt variations also occur higher up. Because course heights change, the builders could not simply repeat one identical setback for every layer. The horizontal retreat required to preserve the intended slope depended on how much each course rose. A tall course had to move inward more than a short one. This required continuous proportional control. The seked was not a single measurement applied mechanically. It was a relationship that had to be recalculated or physically transferred as the masonry changed. The surfaces between blocks also challenged the myth of universal perfection. Some joints, especially in surviving casing and fine chamber masonry, are remarkably tight. Others are wider, irregular, or filled. Ancient mortar was not merely a modern repair or a sign of failure. It helped bed stones, distribute pressure, compensate for uneven surfaces, and stabilize contact between blocks. The structure did not depend on each stone fitting its neighbours with absolute dry precision. The scale of the stones has encouraged claims that gaps could not have been tolerated. In reality, immense blocks can be structurally stable without touching perfectly across every part of their surfaces. What matters is how loads pass through contact points, bedding layers, surrounding masonry, and the wider mass. Recent engineering studies of the pyramid's foundation, chambers, and response to vibration reinforce the idea that the monument behaves as an integrated body rather than as a collection of individually perfect pieces. The king's chamber shows this especially clearly. Its granite walls and ceiling beams are often presented as examples of flawless stonework, yet closer examination reveals cracks, slight displacements, surface changes, and hidden variations in block thickness. Ultrasonic investigation of the lower wall courses suggests that the visible faces do not tell the whole story. Behind them lie uneven rear surfaces, internal reflections, and joints that modern researchers are only beginning to reconstruct. The chamber has survived not because every block is geometrically ideal, but because the surrounding system manages immense loads. Granite beams span the ceiling, relieving spaces rise above, pitched limestone elements redirect pressure. The surrounding masonry distributes weight into the pyramid's body. Even if the traditional term relieving chamber simplifies their exact function, the arrangement demonstrates that structural geometry was layered rather than singular. Cracks in the granite beams are a reminder that the pyramid has never existed outside physical stress. Some damage may have occurred during construction, perhaps when load settled or beams were placed. Other fractures may have developed through earthquakes, thermal changes, or long-term movement. The monument's continued survival does not mean it remained motionless. It has absorbed pressure, vibration, weather, and human interference for thousands of years. The foundation also combines precision with adaptation. The base was leveled with remarkable accuracy, but the builders did not remove every natural rise in the plateau. Bedrock was cut, shaped, and incorporated into the lower pyramid. Some internal areas may contain natural rock far above the formal foundation level. The monument is therefore partly a constructed geometric form and partly a transformed geological mass. This helps explain why a clean diagram can mislead. A diagram shows uniform blocks arranged in perfect layers over a flat plane. The real pyramid contains natural rock, quarried stone of varying dimensions, filling material, local repairs, hidden voids, and zones of different density. It is geometrically coherent without being materially uniform. Construction itself likely produced continual opportunities for drift. Ramps could obscure faces, working platforms could hide casing lines, heavy blocks could settle after placement, ropes could stretch, measuring rods could wear, heat could affect instruments and workers, dust could blur marks. A reference point established at the base might become inaccessible several years later. Every stage introduced error, and the builders had to decide which errors required correction and which could safely remain. Some adjustments can still be detected. Courses may shift slightly to recover alignment. Stone dimensions change around passages and chambers. Local wedges and fitted pieces compensate for irregular spaces. These are not signs that the plan had failed. They show the plan being maintained through practical intervention. The most sophisticated achievement may therefore be tolerance management. Modern engineering depends not on eliminating every deviation, but on deciding how much deviation a system can accept. The Great Pyramid's builders appear to have worked according to the same broad principle, whether or not they expressed it formally. The casing plane required tight control. Core masonry allowed greater flexibility. Chamber roofs demanded special treatment. Passage alignments had to remain consistent. Hidden filling could tolerate rougher work. This hierarchy of precision made the project possible. Without it, the labour required would have become overwhelming. A monument in which every stone had to match the finest granite work would have consumed far more time, material, and skilled effort. By concentrating accuracy at structural and geometric boundaries, the builders created the appearance and performance of a highly ordered whole from components that were often irregular. The contradiction between precision and roughness is therefore only apparent. The pyramid is not precise because every part is perfect. It is precise because imperfect parts were organized within controlled limits. Scholars still debate the exact construction sequence, the degree of adjustment at different heights, and how measurements were transferred as the monument rose. Yet what survives suggests that the builders understood a truth familiar to every large engineering project. Perfection everywhere is unnecessary, but control where it matters is essential. Seen from the plateau, the pyramid presents one clean silhouette. Seen block by block, it becomes a history of compromise. Those two views do not cancel each other. Together they reveal the real achievement, a vast structure in which rough stone, shifting courses, human correction, and mathematical intent were forced into enough agreement to endure. Once imperfection is accepted as part of the monument, the central problem becomes clearer. The builders did not need to avoid every error. They needed to prevent small errors from growing into large ones. A mistake of a few millimeters in one block could be ignored. A mistake of a few centimeters repeated across hundreds of courses could move a face, twist a corner, distort a passage, or shift the intended apex. The Great Pyramid therefore demanded not only measurement, but a system for discovering drift before drift became irreversible. The foundation offered the first and most forgiving opportunity for control. Before the pyramid rose, the builders could still see the whole site. The cardinal axes could be marked across open ground, side lengths could be compared, diagonals could be stretched from corner to corner, bedrock could be cut down, low areas filled, and doubtful points checked repeatedly. At this stage, a line could be moved without dismantling thousands of tons of masonry. Once the lower courses began to cover the plateau, every correction became more expensive. The exact levelling procedure remains uncertain. Water-filled trenches are often proposed because still water creates a horizontal surface, and a channel cut around the footprint could have provided a common elevation reference. Experiments show that such a method is practical, but no complete trench corresponding to a full water-level system has been securely identified around the pyramid. Other reconstructions rely on sighting instruments, plumb lines, straight rods, and repeated elevation checks between fixed points. The builders may have used more than one method, combining local levelling with broader references. Scholars still debate the details, but the finished platform shows that elevation differences were controlled with impressive consistency. Straightness posed a different challenge. A rope stretch between two stakes can define a line, but ropes sag, stretch, and shift. Moisture, fibre quality, tension, and repeated use affect length. Rather than trusting one chord indefinitely, surveyors could compare several measurements, reverse instruments, and re-establish points from independent directions. The ancient practice, sometimes translated as stretching the cord, was not merely ceremonial. It reflects the importance of laying out architectural axes with ropes, stakes, and observed directions. Ropes were useful precisely because they were simple. They could transfer lengths, create arcs, compare diagonals, and establish perpendiculars. A long rope marked at known intervals could function as a portable measuring system, while rigid cubit rods provided shorter, more stable references. Rods could check the rope, and the rope could extend the rod's scale across the site. Each instrument corrected the weaknesses of the other. The royal cubit was not just an abstract unit. It existed physically in rods divided into palms and fingers. A working crew could measure blocks, setbacks, chamber dimensions, and passage widths using a shared standard. Yet no physical standard remains perfect through constant use. Wooden rods warp. Marks wear. Copies differ slightly. A large project therefore required reference standards kept under supervision, with working measures compared against them. Administrative control was part of geometric control. The first courses were especially important because they created the platform from which all later work proceeded. If the lower perimeter was wrong, the error would be carried upward. Casing stones or prepared corner blocks may have served as primary geometric anchors. Their visible faces could define the final slope, even while rougher core masonry filled the space behind them. By setting the outer line carefully and allowing greater flexibility inside, the builders could preserve the monument's form without demanding equal precision from every stone. Corners offered another powerful control system. A pyramid edge should rise in a straight line toward the summit. If corner positions were recorded at successive levels, the builders could compare the actual inward movement with the expected retreat from the chosen seked. A corner that drifted outward could be corrected gradually by increasing the setback of later courses. A corner moving inward too quickly could be eased back. Small corrections distributed across several levels would be less visible and structurally safer than an abrupt change. The broad faces required additional references because corners alone could not guarantee that the centre remained true. Central axes may have been marked on the foundation and transferred upward through temporary sighting points. The subtle concavity of the faces, whether intentional or not, suggests that the middle of each side received particular attention. Surveyors could compare the centre line with the two corners, creating smaller working segments across an otherwise enormous face. Plumb lines were essential wherever verticality mattered. A weighted cord gives a local vertical reference, but the wind can move it, and its usefulness diminishes over great height. Sheltered plumb shafts, temporary frames, and repeated short drops may have provided more reliable checks. Builders did not need one cord hanging from the summit to the ground. They could transfer vertical references upward in stages, much as modern surveyors carry benchmarks through successive floors of a building. Levelling and alignment inside the pyramid demanded even more care. Passages could not be corrected easily once enclosed. Their floors, walls, and ceilings had to maintain direction while surrounding courses rose. A corridor beginning at one elevation and intended to meet another space several meters away required control in 3 dimensions. The builders may have established open trenches or channels first, then roofed them as construction advanced. This allowed the passage line to be checked from above before later masonry sealed it. Chambers were likely treated as independent geometric projects nested within the larger pyramid. Their corners, floor levels, wall lines, and ceiling heights could be checked locally while still tied to the monument's main axis. The king's chamber, built from massive granite blocks, would have required careful sequencing. A block placed incorrectly could not be shifted casually once other stones closed around it. Measurement had to accompany logistics, because the right stone had to arrive at the right level before access disappeared. The rising pyramid gradually removed the open space needed for long sight lines. This may have encouraged the use of external reference stations beyond the base. Fixed points on the plateau could preserve the original axes even after the lower courses were buried. Surveyors standing at those stations might sight along face lines, corners, or central markers higher on the monument. The exact arrangement has not survived, but some external control system would have been useful as the building grew too large to measure only from within its footprint. The pace of construction also affected accuracy. A project moving too quickly risked losing control. A project moving too slowly faced shifting crews, damaged reference marks, and changing administrative priorities. The builders needed a rhythm in which stone delivery, placement, dressing, and checking remained coordinated. Recent computational models of ramp systems emphasize transport intervals and work cycles, but those cycles also had to include measurement. Geometry was part of production, not an activity performed only at the beginning. Specialized teams may have divided responsibility. Quarry workers extracted stone, haulage crews moved it, masons shaped and placed it, surveyors checked lines and levels, scribes recorded deliveries and labor, overseers coordinated sections of the site. The evidence does not preserve a complete organizational chart, yet the scale of the monument makes some hierarchy unavoidable. Precision depended on communication between groups who did not all perform the same tasks. Marks on stones may preserve fragments of that organization. Crew names, orientation marks, quarry notes, and placement instructions helped transform individual blocks into parts of a coordinated structure. Most such markings were hidden once the masonry was completed. Their invisibility reminds us that the pyramid originally contained far more information than its finished surfaces displayed. Error correction was probably quiet and continuous. A course slightly low in one area could be raised with bedding material, a block could be trimmed, a joint could be widened, a later course could compensate for a small shift. A faceline could be adjusted gradually before casing was finished. What survives in the monument suggests not one perfect plan executed without deviation, but a plan defended against deviation through thousands of local decisions. This may be the most difficult part of the Great Pyramid to recover because successful correction erases its own history. When an error is caught early and absorbed, the finished monument does not announce it. Modern surveyors see the final line but not the argument that produced it. The measurement repeated at sunset, the cord tightened again, the stone lowered, raised, shifted, and checked once more. The geometry of the Great Pyramid was therefore not stored only in calculations. It lived in routines. It survived through inspection, redundancy, physical standards, experience judgment, and the willingness to correct before continuing. Millions of stones did not simply obscure the original plan. They forced that plan to be recreated at every level until the monument's final shape emerged from accumulated acts of control. Somewhere in the long disappearance of the Old Kingdom, the Great Pyramid lost its instructions. No complete blueprint survives. No master plan identifies the intended base length, height, chamber sequence, shaft angles, construction stages, or permitted tolerances. There is no surviving document in which Khufu's architects explain why they chose one slope rather than another, how they established true north, or how they intended the internal passages to relate to the exterior. The monument remains, but the written chain of decisions that created it has vanished. This absence is often treated as evidence that the pyramid's methods were deliberately hidden or beyond ordinary explanation. In reality, the loss is not surprising. Construction documents were vulnerable. Plans may have been drawn on papyrus, wooden boards, plastered surfaces, limestone flakes, or temporary grids that had no reason to survive once the project ended. Administrative records could be discarded, reused, burned, buried, or destroyed by moisture and insects. A document created for a working crew was not necessarily preserved as sacred knowledge. The modern expectation of a single complete architectural drawing may also be misleading. The pyramid may not have been governed by one blueprint in the modern sense. Different teams could have worked from separate plans, one for the foundation, another for passages, chambers, casing, quarrying, transport, or ramps. Some information may never have been drawn at full scale because it was carried in measurement systems, templates, verbal instruction, and the experience of specialists. An architect could specify a base in cubits, a height, a seked, and the location of key internal axes without drawing every block. Masons could use rods, cords, corner guides, and prepared profiles to translate those instructions into stone. Many choices were likely made at the site as quarry conditions, block availability, structural behavior, and construction progress became clear. The missing plan may therefore never have existed as one finished object. What remains is a scattered archive written into the monument itself. Cut lines in bedrock show where surfaces were prepared. Sockets indicate the placement of casing stones. Changes in course height reveal shifts in material or method. Passage junctions preserve construction sequence. Unfinished surfaces expose how stone was removed and dressed. Hidden marks identify work crews, orientations, and quarry groups. Each fragment offers part of a process, though none explains the whole. The workmen's inscriptions found in spaces above the king's chamber are especially valuable. These chambers were sealed within the monument and were not created for ordinary visitors. so the painted marks found there were never intended as public decoration. They include crew names associated with Khufu, helping to anchor the pyramid firmly within his reign. The marks also reveal an organized workforce divided into named groups, rather than an anonymous mass laboring without structure. Such inscriptions do not provide mathematical formulas, but they show how planning entered the construction process. Blocks were marked for movement, orientation, ownership, or crew responsibility. A stone arriving from a quarry was part of an administrative sequence before it became part of a wall. Geometry depended on that sequence. A chamber ceiling could not be completed unless correctly sized granite beams arrived at the required stage. A passage could not remain open if surrounding teams filled it too early. The papyri found at Wadi al-Jarf offer another rare glimpse into the world behind the pyramid. Among them is the journal associated with an official named Mera, whose crew transported limestone by boat during Khufu's reign. The record does not describe the pyramid's geometry or reveal its construction method. It is far more ordinary, noting movements, deliveries, and travel between locations connected with the royal project. Its ordinariness makes it powerful. The Great Pyramid did not emerge from one unexplained act of technical genius. It depended on schedules, harbours, waterways, crews, supplies, and officials recording daily work. The journal shows a state capable of coordinating material over distance and time. It does not solve the monument, but it replaces vague wonder with the machinery of administration. Other evidence comes from the wider Giza landscape. Workers' settlements, bakeries, storage facilities, animal remains, tools, and administrative seals reveal a permanent support system around the royal building projects. The workforce had to be housed, fed, organized, and supplied. The project required not only skilled stoneworkers but cooks, boat crews, rope makers, scribes, surveyors, haulers, tool specialists, and supervisors. A geometric plan could succeed only within that social structure. A perfectly calculated slope was useless if stone arrived irregularly. Crews lacked food, or tools could not be repaired. The precision visible in the monument reflects institutional precision as much as mathematical ability. Comparable pyramids preserve another form of lost documentation. The monuments built before and after Khufu can be read as experiments in stone. The step pyramid at Saqqara records the transformation of the royal tomb into a rising stone monument. Sneferu's pyramids at Meidum and Dashur show changing slopes, internal arrangements, masonry techniques, and structural lessons. The bent pyramid, with its altered angle, preserves a major design revision that no written report explains. These monuments form a practical archive of development. Khufu's pyramid did not appear without precedent. It followed decades of large-scale construction, during which Egyptian builders tested foundations, casing, chamber roofs, passage systems, slopes, and methods of raising stone. Failures, cracks, collapses, and revisions could teach more than ideal diagrams. The Great Pyramid inherited this accumulated experience. Later pyramids offer their own comparisons. Many preserve similar basic elements but differ in size, quality, internal planning, and construction materials. Some contain pyramid texts, yet these religious inscriptions do not explain engineering. Others have deteriorated badly, revealing how core techniques and material choices affected survival. The Great Pyramid's exceptional state is not simply the consequence of its shape, it reflects the quality of its foundation, masonry mass, stone selection, and structural planning. Ancient mathematical papyri add another indirect clue. They preserve problems involving slopes, volumes, areas, fractions, and storage calculations. These texts are later than Khufu's reign, and scholars still debate how far their methods can be projected backward. They nevertheless show that Egyptian mathematics was practical, procedural, and closely tied to administration and construction. Calculations were often expressed as worked examples rather than abstract proofs. This style may explain why the Great Pyramid's planning leaves so little theoretical trace. The builders did not need a philosophical treatise on geometry. They needed methods that produced repeatable answers, a rule for slope, a standard cubit, a way to square corners, and procedures for checking level were more useful on the plateau than an abstract demonstration of why those methods worked. The monument may also preserve evidence of changing plans. The subterranean chamber, Queen's chamber, and King's chamber are often interpreted as successive burial schemes. Though this sequence is not universally accepted, if the design changed, then the missing documents would have included revisions, abandoned instructions, and new calculations. The final pyramid may represent not one immutable concept, but a project that evolved while remaining within a stable external form. That possibility makes the absence of plans even more important. Without them, modern researchers attempted to assume that every feature was present from the first day of construction. Yet large projects often change, access needs alter, structural problems emerge, ritual requirements develop, a chamber can be abandoned, a passage extended, or a shaft redirected while the outer design remains broadly unchanged. No surviving fragment tells us who possessed the authority to approve such decisions. Later, Egyptian tradition remembers figures associated with wisdom and building, but the historical identity of Khufu's principal architect remains uncertain. Hemionu, a high official whose large mastaba stands near the pyramid, is often considered a strong candidate for a leading role. Even so, the monument must have depended on many specialists rather than one solitary genius. The search for a lost master architect can obscure the collective nature of the work. Surveying knowledge may have been held by one group, quarry expertise by another, and ritual requirements by priests and royal officials. Planning emerged through coordination among institutions whose records are mostly gone. The missing plans of Giza therefore create a genuine boundary around modern knowledge. Archaeology can reconstruct dimensions, sequences, tools, settlements, and transport networks. Experiments can test how ropes, sledges, ramps, and sighting methods perform. Computer models can calculate labor and timing, but none of these can reproduce the builder's intentions with complete certainty. The silence should not be filled with impossible technology simply because ordinary documentation has vanished. Nor should the remaining questions be dismissed as already solved. The pyramid survives between those extremes. Its blueprint is scattered across stone, landscape, mathematics, administrative fragments, and neighbouring monuments. Enough remains to show that the builders possessed a powerful and practical system. Not enough remains to watch that system working from beginning to end. The absence of a complete blueprint creates an open space around the Great Pyramid, and open spaces attract patterns. Once the original design logic is partly lost, later observers begin supplying their own. A side length becomes a code, a passage angle becomes a date, a chamber dimension becomes a map of the heavens, a geographic coordinate is compared with the speed of light. The pyramid's height is converted into modern units, scaled upward and linked to the size of Earth. Some of these relationships are mathematically real. The problem is that reality alone does not establish intention. The Great Pyramid is especially vulnerable to numerical interpretation because it offers so many dimensions. There are 4 base sides, 2 diagonals, 1 reconstructed height, 4 face apothegms, edge lengths, passage slopes, chamber widths, chamber heights, shaft angles, course levels, distances between rooms, and countless positions measured from different reference points. Each quantity can be expressed in cubits, meters, feet, inches, degrees, fractions, or ratios. Once enough numbers are available, it becomes almost inevitable that some will resemble famous constants, astronomical periods, geographic measures, or historical dates. This is not a flaw in mathematics, it is a flaw in the way evidence can be selected. A strong historical claim begins with a plausible ancient unit, a known design method, and a relationship that appears consistently across the monument. A weak claim begins with the desired result and searches backward for measurements that produce it. If one side length fails, another may be chosen. If the surviving height is inconvenient, the reconstructed height is used. If meters do not work, inches may. If the result is still imperfect, a scaling factor is introduced. The calculation can become more exact while the historical argument becomes less secure. The pyramid's damaged state makes this process easier, because the casing is mostly gone and the summit is missing. Several dimensions must be reconstructed. Small variations can be defended as alternative surveys, erosion allowances, or corrections for the lost outer surface. A pattern seeker may choose the reconstruction that fits best, then present the result as though it were the only possible measurement. The uncertainty that should weaken the claim is turned into flexibility that strengthens it. Claims involving modern geographic coordinates offer a clear example. The latitude of the Great Pyramid can be written in decimal degrees, and part of that number resembles the numerical value of the speed of light when expressed in meters per second. The resemblance is striking when displayed without context, yet decimal degrees are a modern convention. Meters are modern units. The prime meridian is historically chosen. The number of decimal places selected matters. The pyramid occupies an area rather than one dimensionless point, so a specific coordinate must also be chosen from among many possible positions across the monument. The match says more about modern numerical systems than about Old Kingdom planning. Similar problems appear when the pyramid is said to encode Earth's circumference. The monument's height can be multiplied by a large-scale factor to approach the planet's polar radius or circumference. But the scale factor is selected after the comparison is noticed, and small changes in reconstructed height affect the result. Ancient Egyptians were capable observers of land, sky, and seasonal cycles, but there is no secure evidence that Khufu's builders possessed the modern geodetic measurements required by the strongest versions of these claims. Astronomical interpretations are more complicated because the pyramid was genuinely connected to the sky. Its cardinal orientation is real. Its northern direction had religious significance. The shafts may relate to stellar or solar symbolism. The arrangement of the Giza pyramids has therefore been compared with the stars of Orion's belt, especially because Orion was associated with Osiris in later Egyptian religious thought. The visual resemblance is suggestive 3 major pyramids, 3 prominent stars, with one pyramid offset from the line formed by the other 2, yet the scale, orientation, relative sizes, chronology, and surrounding architecture do not produce a perfect celestial map. Supporters can improve the match by rotating, reflecting, or rescaling the pattern, but each adjustment increases the danger of fitting the evidence to the theory. Scholars still debate the astronomical symbolism of Giza, but the claim that the plateau was designed as an exact terrestrial copy of Orion remains unsupported. This does not mean the sky was irrelevant. Egyptian royal architecture was saturated with celestial meaning. the king's afterlife, the circumpolar stars, the sun, and the ordered horizon all shaped how monuments were understood. The mistake is to assume that symbolic association requires a precise star chart. Ancient architecture can evoke the heavens without reproducing them as a measured map. Lost technology theories follow a similar path. The pyramid's close alignment, granite work, and enormous scale are presented as impossible with documented tools. From that premise, the argument moves toward advanced machinery, vanished civilizations, external teachers, or technologies unknown to archaeology. Yet the premise is usually exaggerated. Copper tools, stone pounders, abrasives, sledges, boats, ropes, levers, ramps, and organized labor can explain much of the physical work, though scholars still debate the exact combination and sequence. The strongest mystery is not whether stone can be cut or moved. Experiments and surviving evidence show that it can. The unresolved questions concern efficiency, site organization, ramp geometry, lifting methods at different heights, and how the builders maintained control over time. These are serious problems, but uncertainty about the precise method does not prove the use of impossible machinery. Marks left by cutting and drilling are sometimes treated as evidence of high-speed tools. Granite surfaces can display grooves, cores, and striations that appear dramatic in photographs. However, abrasive sand used with copper saws or tubular drills can produce effective cutting action, even when the metal itself is softer than the stone. The process is slow, labor-intensive, and technically demanding, but slowness is not impossibility. Modern observers often underestimate what repeated effort can achieve when supported by a large state over many years. The same caution applies to block fitting. Photographs commonly focus on the finest joints and imply that every stone in the pyramid matches that standard. In reality, quality varies greatly. Exceptional masonry exists, especially in chambers and surviving casing work. But rougher joints and irregular blocks are widespread. Selective images can transform a hierarchy of workmanship into a myth of uniform machine precision. Numerological interpretations go still further. Chamber dimensions are linked to sacred numbers, prophetic calendars, dynastic events, or future dates. Passage lengths are converted into inches and read as timelines. The method can always be extended because every point along a corridor offers another possible number. Failed predictions are then revised by changing the starting point, unit, or symbolic key. What these systems lack is independent constraint. A valid interpretation should explain why a particular unit was used, why a particular measurement mattered to the builders, and why the same rule works elsewhere without adjustment. If the rule is discovered only after hundreds of comparisons, its apparent success may be statistical rather than historical. The Great Pyramid does contain meaningful patterns. Its cardinal alignment is deliberate, its square base is deliberate, its slope follows a coherent ratio. Its passages and chambers are organized through planned axes and elevations. These relationships are supported by construction logic and Egyptian practice. The difficulty begins when every additional resemblance is given equal weight. Human beings are skilled at finding order, especially in monuments that seem to demand explanation. The pyramid rewards that instinct because its geometry is both simple and rich. A few primary dimensions generate many secondary ratios. Damage introduces uncertainty. Modern units create new combinations. Cultural symbolism invites celestial comparison. Together, these conditions form an almost perfect engine for numerical mythology. The safest response is not to reject every unusual relationship, but to ask what evidence would distinguish intention from coincidence. Does the ratio arise from an Egyptian measuring system? Is it repeated? Does it assist construction? Is it supported by texts, tools, or comparable monuments? Does the claim survive reasonable changes in measurement? If not, the pattern may still be beautiful, but beauty is not proof. The Great Pyramid does not need secret codes to remain extraordinary. Its documented geometry, material scale, and organizational demands are already enough. The patterns that multiply around it often reveal less about Khufu's builders than about later generations unwilling to accept that human achievement can be remarkable without being supernatural. The monument invites calculation, but it also demands restraint. Not every number hidden in its stones was placed there by the people who raised them. The Great Pyramid's oldest questions now meet some of the newest instruments ever brought to archaeology. For centuries, investigators searched the monument by entering passages, clearing shafts, drilling through walls, measuring visible surfaces, and comparing the plans left by earlier explorers. Those methods revealed much, but they were limited by the obvious problem that the pyramid cannot simply be taken apart. Most of its interior is inaccessible masonry. A wall may conceal another layer of stone, a joint, a cavity, or nothing unusual at all, and destructive testing carries risks that no responsible investigation can ignore. Modern research therefore increasingly depends on technologies that can look through the monument without opening it. This shift has changed the language of discovery. Researchers now speak of density anomalies, resistivity contrasts, ultrasonic reflections, thermal differences, and cosmic ray muons. The terms sound remote from ropes, cubits, and limestone blocks. Yet they address the same fundamental problem: how space is arranged inside the pyramid. Each technique reads the monument differently. None offers a complete transparent image. Together, they can reveal geometry that the builders sealed away more than 4,000 years ago. Muon imaging provides one of the most dramatic examples. Muons are high-energy particles produced when cosmic radiation strikes Earth's atmosphere. They pass through matter more easily than ordinary light or X-rays, though dense material absorbs more of them than empty space does. Detectors placed around or inside a large structure can record the number and direction of muons arriving through the stone. If an area allows more particles to pass than expected, it may indicate a void or region of lower density. The method does not produce a photograph of a hidden chamber. It creates a statistical map that must be interpreted. Detector position, exposure time, surrounding masonry, structural models, and possible noise all affect the result. Even so, muon measurements have transformed the investigation of the Great Pyramid because they can examine vast volumes of stone that are otherwise inaccessible. Near the northern face, muon observations helped identify a corridor-shaped structure behind the chevron stones above the original entrance. The space extends inward for several meters and has a roughly corridor-like cross-section. Later, non-destructive studies using radar, ultrasound, and electrical resistivity added independent evidence. By combining techniques that respond to different physical properties, researchers strengthen the case that the anomaly represents a real architectural space rather than a misleading reading from one instrument. This north-face corridor raises an immediate question about purpose. It may reduce pressure above the entrance area, serve as a relieving space, represent an unfinished access route, or belong to a construction sequence no longer understood. Its location near the prominent chevron blocks suggests a structural relationship, but the evidence does not yet establish one explanation. The corridor is real, its meaning remains uncertain. That distinction is essential. A new void does not automatically reveal a secret chamber. It does not prove the existence of a lost royal burial, an archive, or hidden technology. The popular imagination moves faster than the data. Archaeological interpretation must remain slower. Dimensions, orientation, construction details, and connections to known spaces must be established before function can be judged. Electrical resistivity tomography offers another way to examine the same region. Small electrical currents are introduced through sensors, and researchers measure how strongly the material resists their movement. Solid limestone, fractured stone, mortar, moisture, and empty cavities behave differently. By taking many measurements from different positions, a three-dimensional model of changing resistivity can be constructed. The method is sensitive to conditions that have nothing to do with architecture: salt, humidity, cracks, material variation, and surface contact can all affect readings. This is why one technique rarely settles the matter. When resistivity, radar, ultrasound, and muon results point toward the same shape, confidence grows. Multimodal imaging does not eliminate uncertainty, but it narrows the range of plausible explanations. Ultrasound works at a smaller and more intimate scale. Sound waves travel through stone, reflecting from joints, cracks, rear surfaces, and changes in material. In the King's Chamber, recent ultrasonic testing has examined the lower granite wall courses to estimate block thicknesses and identify hidden interfaces. The visible wall appears as a series of carefully fitted granite faces. Behind those faces, the masonry may be more irregular than early plans assumed. These findings matter because many older reconstructions treat the chamber walls as simple, rectangular blocks extending backward in predictable ways. Ultrasonic reflections suggest that some blocks have uneven rear surfaces, complex joints, or thicknesses that vary from one location to another. The geometry hidden behind the polished interior face may not match the neat diagrams used for generations. That does not imply careless building. A finely controlled visible chamber could be created while allowing less regular geometry behind the wall, provided the surrounding masonry remained stable. Once again, the pyramid reveals a hierarchy of precision. The inner surface mattered for ritual, appearance, alignment, and perhaps the placement of the stone sarcophagus. The concealed rear surfaces primarily had to transmit load and fit within the surrounding structure. Material analysis further complicates the geometric picture. The King's Chamber is built largely from granite transported from Aswan, while other internal spaces rely on limestone of different qualities. Mineral changes, salt deposits, surface weathering, moisture movement, and microscopic deterioration affect how waves, currents, and radiation pass through the stone. A scanning instrument is not reading pure geometry. It is reading geometry through materials that have aged for millennia. This is why conservation research and architectural research now overlap. To understand an anomaly, investigators must know whether it reflects an empty space, a crack, a mortar-filled joint, a change in stone type, or a zone altered by moisture and salts. The Great Pyramid is not a frozen mathematical object. It is a physical body whose materials continue to change. Structural modeling adds another layer. Engineers can simulate how the foundation, chambers, relieving spaces, cracks, and masonry mass respond to gravity or vibration. Studies of earthquake resilience examine natural frequencies, stress concentration, and the role of the bedrock beneath the monument. These models help explain why the pyramid has survived repeated seismic events and why damage appears in particular places. Yet a model is not the monument. It depends on assumptions about block contact, internal density, hidden voids, material strength, and the continuity of masonry. If the internal geometry is incomplete, structural simulations must simplify it. New scans can therefore change the models, while the models help researchers decide which hidden features matter most. The same interaction appears in construction research. Computational studies can test whether proposed ramps fit along the pyramid's edges, how many hauling cycles are required, and whether stone delivery rates match a plausible construction period. A model may show that a particular system is mechanically possible, but possibility is not proof of historical use. Ramps, platforms, and temporary works were removed, buried, or recycled. Their geometry survives less clearly than the pyramid itself. A recent edge-integrated multi-ramp model demonstrates how computing can transform an old argument. Instead of drawing one speculative ramp, researchers can estimate loads, haul distances, traffic intervals, changing heights, labour cycles, and the way ramps might be incorporated into the monument's sides. The results suggest that a large-scale construction schedule need not be impossible. Yet the model still depends on assumptions about workforce size, friction, seasonality, stone distribution, and the exact shape of the temporary infrastructure. Another proposal interprets the Grand Gallery and connected passages as parts of a counterweight system. The geometry of the interior is used to reconstruct sliding masses, rope paths, and lifting operations. The idea is ingenious and testable in certain respects, but direct evidence remains limited. The gallery's known ritual and architectural roles cannot be discarded simply because a mechanical function is possible. A space may have served several purposes, or the proposed mechanism may never have existed. This is the pattern modern technology repeatedly reveals. A new instrument resolves one uncertainty and creates several others. Muons confirm a void, but not its purpose. Ultrasound shows hidden block boundaries, but not the sequence of their placement. Resistivity maps an anomaly, but must distinguish cavity from material change. Structural models explain stability while relying on incomplete internal data. Construction simulations demonstrate feasibility without identifying the actual method. The Great Pyramid is therefore becoming better known and less simple at the same time. Its internal map is more detailed than ever, but each added corridor, irregular block, density change, or structural response weakens the old image of a perfectly uniform stone mountain. The monument becomes a layered system built, altered, stressed, damaged, and preserved across time. Modern scanning does not remove the ancient mystery, it changes its scale. Earlier explorers asked whether hidden chambers existed. Researchers now ask how thick a particular granite block is behind its visible face, how two imaging methods can be fused, whether a small resistivity change reflects moisture or emptiness, and how a concealed corridor relates to load above the entrance. The questions have become narrower, more technical, and in many ways more profound. The pyramid is no longer waiting for one dramatic discovery that explains everything. It is being reconstructed piece by piece, through probabilities and overlapping signals. The geometry still does not fully add up because the equation itself keeps gaining new terms. After centuries of measurement, excavation, calculation, scanning, and argument, the Great Pyramid stands in a strange position. More is known about its geometry than at any previous moment, yet the monument has not become completely explainable. Its base can be reconstructed within narrow limits. Its orientation can be measured to tiny fractions of a degree. Its slope can be expressed through a historically plausible seked. Its internal corridors can be mapped. While hidden spaces can be detected through particles arriving from the upper atmosphere, Engineers can model its structural behavior, and computers can test whether proposed ramp systems could have delivered stones at the required pace. The numbers do add up in many important ways. What remains uncertain is how those numbers were selected, transferred, checked, corrected, and transformed into a structure weighing millions of tons. The strongest conclusions begin with the simplest geometry. The builders intended a square base aligned closely with the cardinal directions. The four sides are not identical, and the corners are not perfectly square, but their differences are remarkably small compared with the monument's scale. This was deliberate surveying, not chance. The original casing established smooth outer faces rising at a controlled slope. That slope is compatible with the seked of 5 palms and 2 fingers for each royal cubit of rise, a practical relationship rooted in Egyptian measurement rather than modern trigonometry. These points require no lost civilization, advanced machinery, or secret mathematical revelation. Egyptian builders possessed the necessary foundation standardized units, ropes, rods, plumb lines, leveling practices, astronomical observation, stoneworking skill, administrative control, and generations of experience gained from earlier pyramids. None of those elements is individually impossible. Their power lies in coordination. The monument's famous pi relationship remains genuine but ambiguous. The base perimeter compared with twice the reconstructed height yields a value close to pi. If the base and height were intended as roughly 440 and 280 royal cubits, the relationship becomes the familiar approximation of 22 divided by 7. Yet the same result follows naturally from the proposed seked. The builders could have chosen a practical slope and produced the circular relationship as a consequence. They may have recognized and valued it, or they may not have treated it as a separate constant at all. The golden ratio presents an even less secure case. A phi-like relationship appears between the slant height and half the base, but that slant height is determined automatically once the height and base are fixed. There is no surviving Old Kingdom evidence that the builders designed around phi as an abstract principle. The proportion may have contributed to the pyramid's visual harmony, but claims of deliberate encoding go beyond what the surviving record can demonstrate. The geometry of the faces is similarly unresolved. The shallow concavity dividing each face may have been intentional, perhaps assisting visual appearance, structural behavior, or surveying. It may instead result from the arrangement of the core, long-term settlement, earthquakes, or uneven casing removal. The effect is real enough to observe under certain lighting, but the loss of the original outer surface prevents certainty. Inside the pyramid, the evidence becomes more complex. The descending and ascending passages, the grand gallery, the chambers, shafts, relieving spaces, and newly confirmed northern corridor show that the monument was planned in 3 dimensions. These features could not have been improvised after the exterior was complete. Their positions had to be established while construction advanced around them. Yet internal purpose remains harder to establish than internal position. The king's chamber clearly belonged to the royal funerary program, but the exact functions of the queen's chamber, shafts, subterranean chamber, grand gallery, and north face corridor remain debated. Structural, ritual, logistical, and security needs may overlap. A passage could guide movement during construction and later acquire a funerary role. A void could protect an entrance from load without serving as a route. Ancient architecture does not always separate practical and symbolic functions as cleanly as modern analysis prefers. The mechanics of construction remain the largest open question. Broad evidence supports the use of ramps, sledges, ropes, levers, boats, prepared roads, and organize teams. The ancient Aramat branch of the Nile helps explain how stone and supplies reached the pyramid fields. Mira's journal confirms that high-quality limestone travelled by water during Khufu's reign. Workers' settlements and administrative remains reveal the support system behind the monument. What remains unknown is the exact arrangement used at every height. A straight ramp may work efficiently at lower levels, but become impractically large as the pyramid rises. Turning ramps, zigzagging routes, edge-integrated systems, levers, and counterweights each solve parts of the problem while creating new difficulties. Recent computational models show that edge-based ramps could fit plausible schedules and transport rhythms. Counterweight proposals attempt to explain architectural features such as the Grand Gallery. These models are valuable because they transform vague claims into testable mechanics. But feasibility is not historical proof. The construction method may never reduce to one system. Different stages likely required different solutions. Heavy blocks near the base could move along broad ramps. Higher courses may have used narrower paths, turning platforms, levers, or short lifting stages. Granite beams destined for the king's chamber demanded different handling from ordinary limestone core blocks. The search for one elegant mechanism may be less realistic than a sequence of methods adjusted as the workplace changed. The same principle applies to precision. The builders did not maintain one universal standard across every block. They established a hierarchy: foundation lines, corners, casing surfaces, passage axes, chamber floors, and critical structural elements received close control. Hidden core masonry tolerated wider joints and irregular shapes. Mortar, packing stones, and local correction absorbed differences. The pyramid's accuracy emerged at the level of the whole, not through machine-like perfection in every component. This is perhaps the clearest answer the evidence provides. The Great Pyramid was not built by eliminating error, it was built by managing error. The surveyors created redundant references. Masons corrected deviations before they accumulated. Overseers concentrated effort where small mistakes threatened the larger plan. The monument's clean silhouette arose from countless local decisions whose individual traces are mostly invisible. Its durability also reflects the relationship between geometry and geology. The builders adapted the natural plateau rather than replacing it with an entirely artificial platform. Bedrock became part of the foundation, and perhaps part of the lower core. The pyramid's broad base, inclined faces, massive masonry, chamber roofing, and load-distributing spaces helped it survive long-term pressure and seismic disturbance. Recent structural studies suggest that its stability must be understood as an interaction among stone, foundation, voids, material properties, and overall form. Still, survival should not be confused with immunity. Granite beams are cracked. Stone surfaces accumulate salts and mineral changes. Joints shift. Earthquakes and quarrying have altered the monument. The casing is mostly gone. The summit has vanished. The pyramid that modern researchers measure is not the exact body completed in Khufu's reign. Every reconstruction carries uncertainty. That uncertainty sets a limit on claims of extreme numerical precision. It is reasonable to say that the pyramid was laid out and oriented with astonishing care. It is not reasonable to pretend that damaged dimensions can establish hidden constants to many decimal places. The more exact a claim becomes, the more carefully its assumptions must be examined. The Great Pyramid's geometry therefore occupies a middle ground that is less sensational than impossibility and more compelling than complete solution. Its main dimensions can be explained through Egyptian mathematics and surveying. Its construction can be approached through plausible technologies and large-scale organization. Its internal system is increasingly visible through modern imaging, yet the complete sequence of decisions remains lost. No master blueprint has survived to identify which number came first. Perhaps the architects began with a base measured in whole cubits and selected a suitable seked. Perhaps height held special importance. Perhaps the proportions were refined through inherited practice from Sneferu's pyramids. Perhaps aesthetic, ritual, structural, and logistical considerations converged on the final form. Several explanations can fit the same stones because the design process leaves fewer traces than the finished design. This is why the Great Pyramid continues to resist finality. It is not a riddle with one concealed answer waiting behind a wall. It is the remains of a vast human process. Its mathematics was inseparable from workers, boats, quarries, food, astronomy, state power, religious belief, and the uneven limestone plateau beneath it. To understand the monument fully would require recovering not only its measurements, but the living system that maintained them. The numbers reveal enough to dismiss the claim that the pyramid lies beyond human capability. They also reveal enough to reject the idea that nothing important remains unanswered. Between those conclusions stands a more difficult truth. Ancient Egyptian builders possessed methods powerful enough to create the monument, but the detailed operation of those methods has not survived. Their success remains visible. Their procedures survive only in fragments. The Great Pyramid's geometry adds up as engineering, but not yet as history. The shape can be calculated. The original dimensions can be approached. The likely tools can be identified. What cannot be recovered completely is the sequence of judgment that held everything together when a line was checked, why a slope was chosen, where an error was tolerated, when a design changed, and how thousands of people shared one geometric intention across decades of work. That missing human chain is the true unanswered equation. The pyramid does not prove that its builders possessed impossible knowledge. It proves that knowledge can be practical, collective, and extraordinarily effective even when the documents explaining it disappear. Its stones preserve the result while hiding the method, leaving a monument that is mathematically comprehensible and historically unfinished. As the light fades across Giza, the pyramid loses the details that have occupied surveyors for generations. Individual blocks disappear into shadow, cracks, joints, missing casing sockets, and uneven courses merge into one darkening face. From a distance, the imperfections vanish first. The monument becomes a triangle again, calm and apparently simple against the evening sky. The people who measured its foundation are gone. So are the crews who tightened cords across the plateau, the officials who counted stone deliveries, the masons who adjusted one course to recover a drifting line, and the observers who waited for a shadow or star to reveal north. Their names survive only rarely, and their calculations are mostly lost. Yet their decisions remain suspended in the form they created. Time has taken the polished casing, the summit, the temporary ramps, the harbour traffic, and the noise of construction. It has left the geometry behind, though even that survives imperfectly. Modern instruments now pass sound through granite, current through limestone, and cosmic particles through the body of the pyramid. They find new edges in the darkness, but never the complete memory of how those edges came to be. Perhaps that is why the monument remains so powerful. It is neither fully silent nor fully readable. It tells enough of its story to show what human beings accomplished, while withholding the ordinary gestures that made the accomplishment possible. A rod placed level, a cord pulled straight, a stone shifted by a hand's width, a mark checked once more before the next course began. The Great Pyramid endures not as proof that the ancient world escaped the limits of human knowledge, but as proof that those limits can be pushed so far that later ages struggle to reconstruct the path. Beneath the stars, its four sides still face the world with slight, measurable imperfection, and inside that narrow margin between intention and error, an entire vanished system of knowledge continues to breathe,